In this lecture, we're going to talk about minimum risk, regression, and classification. So we're going to transition now. We've talked about two regression techniques, and we've talked about some of the issues evaluating those regression techniques. We're going to talk today about what is kind of theoretically the best way to fit a regression technique or fit a regression method, and how the existing methods that we've learned fit into that. And then we're going to talk about a similar thing for classification. So we're going to introduce classification, and then we're going to move on, and we're going to talk about kind of similarly what's the optimal thing to do there. And then we're going to start learning some methods with kind of prospectively the viewpoint of how this fits into kind of the optimal way to build a classification method. So let's start with regression. So this is going to be kind of one of the, we're going to do mostly theory for the first good part of this, or most of the lecture today. We're going to slowly kind of ease out of these more theoretical lectures into a couple more methods-y lectures. We're just talking about some methods and how they're built. But this lecture and maybe a little bit of the next one will be a little bit theoretical. So for regression, the kind of question that we want to answer is, what is the best f hat? What is the best regression function that we can build? So the viewpoint of statistical learning is that our data, x and y, have some joint distribution. What exactly that joint distribution is, we don't exactly know, but they have some joint distribution. And what we want to do is we want to, let's say we want some f hat. So maybe we should say something about f. Let's say they have some joint distribution, and y is some f of x. So we know at least something about how they're related to each other. There's some unknown f, some true data generating function that relates y to our x's through y's f of x, but x is random, and so y is going to be random. So it's not like when we observe our actual data, we draw from this distribution of x and y. So it's not like we're always going to get the same value of y for the same value of x, right? Because we're taking random draws. And what we want here, so let me write this now, is we want some f hat that is an estimate of f, so that y is going to be kind of approximately f hat of x. And it's a bit abusive of notation, a bit vague, but basically the idea is that for new draws of from our distribution, we can predict the y if we just draw the x, right? If we just get the x. And let's say we do this, we construct f hat by defining a loss L, so L is just some, let's say, some real valued function. Sure, L is a real valued function. I guess X could be multivariables. Could be multivariate random variables. So I suppose we could say that whatever the dimension. So x might be a p-dimensional vector. So I guess our loss could be from rp to r, right? And this loss basically tells us how well y is approximated, or how well f hat does at approximating y from x. And we choose f hat by minimizing over possible f's the risk, which we define as the expected loss of some candidate f. So it should maybe be clarified here. Maybe we will call our so there's two f's here. There's the true underlying f, and then there's just the f that we're optimizing over. Maybe you could call this thing f star, which is like the true f. It doesn't really matter notationally what you call it, right? But we're optimizing. So I mean, f star is the true f. F hat is our prediction, and we get f hat by minimizing the risk of this loss, and the risk is the expected loss. For some candidate f, our loss is L of f, and our expected loss is the expectation of that, right? So, so L of f, for example, let's say so far we have looked at L of f as the squared loss, which is L of f is y minus f of x, right? So this is all kind of review. And in reality, what we do is, so we'll just write this as a sidebar. Reality is that we have our training data. Right, we get our training data, x and y ends, and we minimize the empirical risk, which is basically an estimate of our risk, right, L of f. So basically this kind of average, and in the case of squared loss, this would be, say, yn minus f of xn quantity squared, right? The sum of those. Of course, we call this the MSE. But you could also call it the empirical risk. Basically, right, it's an estimate of this expectation, right? We don't know the true distribution, so we draw a bunch of things from a distribution, and we estimate the quantity, right? Just in the way, we don't know the true mean, we draw data from our distribution, we use x bar to estimate the mean. Same deal. Okay. So that's the setup. So let's look at, theoretically, if we were to minimize this risk, is there some kind of theoretical answer if we use the squared error loss, what our best answer would be? And the answer is basically yes. For something very nice, like the squared loss, we can get kind of a theoretical answer. And you'll see what I mean by kind of. So the quantity that we're interested in, let me just write what is theoretically f hat. And our quantity of interest is this thing, right? Is our risk. This thing, actually, let me move this to the side here. Let's just move this bad boy here, right? So this is the expected, in our case, if we're going to use the squared error loss, let's say for squared loss, this is y minus fx quantity squared, right? Now, let's bring back some terrible flashbacks from 451. Recall that if I want to calculate, for example, the expected value of x, is that what I want to calculate? Yes. If I want to calculate, say, the expected value of x, I can use my iterated expectation formula. So this would be the expected value over x of the expected value of y given x of this. All right. So that is our iterated expectation formula. Well, it turns out there is a kind of similar, there's no particular reason why we need to restrict ourselves here just to x, right? So you can come up with a similar kind of thing. For example, if I wanted the expected value of x by y, I could look at the expected value with respect to x of the expected value with respect to the conditional distribution y given x of xy, and that is also true. So although it's commonly written in terms of just say the expected value of x, we can play a similar game here with multiple variables. And so let's look at what that does to our equation here. So this is just an analogy. I'll show you. I mean, you'll basically be able to see that we're basically using, if you go back to the proof iterated expectation, we're kind of using that, right? So our definition here of this expectation, let's say, for just the sake of argument, well, we won't really care. We're just going to kind of pretend that x is univariate. It doesn't really matter. It would just be more integrals here. Not a big deal, right? So this would be, right, the integral of the function, y minus fx squared, and then we'd multiply that by the density function for x and y. So this p of xy is my density function. So when I said way back up here that x and y have some joint distribution, right, let's call that pxy, my bivariate distribution. And then I multiply by that, and then I do, right, dx dy, right? So this is my definition of bivariate or whatever multivariate expectation, right? And so very much if you think about kind of what's going on in iterated expectation, if you go back to the proof of that, for example, we can play some games here. P of xy could be written as P of y given x times the marginal of x, right? So that the joint is the conditional times the marginal, right? And of course I have my dx dy. And then I can just play some rearrangement game here, right? So I have an integral, I have another integral. So this is basically the proof of iterated expectation. And then I have my density of y given x, right? The reason I didn't use f for density is obvious. We have this other f here. I'll use p for probability. And I'm going to put my dy here. I'm just going to bring that in. So this is my inner integral. And then I have dx here, right? So the aside is that this is the expected value of y minus fx quantity squared given x, right? So the inner integral is y. I could write it how I did before, right? The inner integral is respect to y given x, and the outer integral, or outer expectation, is respect to x, right? So basically, my iterated expectation here. So I could have done this in one step, but I like showing out the calculus a bit more. Okay, so that is my risk, right? This is our quantity of interest, right? So we want to minimize this risk. That will give us f hat, okay? And I've shown that you can rewrite it as the expected value of x of the expected value of y given x of that quantity. Okay, good. So let's just talk for a second here about what we're doing, right? Because what we're doing is we want to have f hat be the minimizer of this risk, right? So let me just write this up in the corner here. This is going a bit slow through this because this is a pretty, not complicated, but it takes a lot of really careful thinking about exactly all the moving parts here. And once you get it, you go, oh, yeah, okay. But it does, this is not a trivial, it takes me always a bit to get this all straight in my head, right? So let's just write what we're doing here, right? So this is our goal. We're minimizing the risk, right? And what does that mean, right? We're trying to find, we're picking a function f, right? We're picking the function f, and f is just some real valued function. This is nothing fancy, right? In our case, I mean, I guess generally it could be rp to r, but you can think of it just as a real valued function. Right? So p is equal to 1, right? So we're picking a function. We're searching over all these different functions. I'm being a bit vague on exactly what we're searching over, but we're searching over this whole space of functions, and we're trying to minimize this quantity. And so what does it mean to search over functions? What does it mean, right? So basically, I'm going to build up a function. I would evaluate the empirical risk. I'd build up another function, evaluate its empirical risk, right? And you can imagine doing this for the infinite possibilities of function. So what does it mean? What is a function, right? So everyone always complains that, oh, we have to have 214, you know, this stuff is useless, right? But it's useful for, you gotta really think about what is a function actually, right? All a function is it relates inputs to outputs, right? A function is not a curve. A function doesn't have to be differentiable, doesn't have to be continuous, doesn't have to be anything nice. All a function is I have some x's, and I'm going to tell you what the y value is, right? Y is f of x, right? So f of x is just a number, x is a number, right? And if I want to build a function, so let's together build a function, right? What do I have to do to build a function? Not really that much complicated, right? At a value of x, I pick my value of x, and then I say, okay, the corresponding value of y is going to be there. And for another value of x, I say the corresponding value of y is going to be there. And for this value of x, I say the corresponding value of y is there. Maybe the corresponding value of y is there. It's here, right? And then just for each value of x, I'm picking my corresponding value of y, right? That's all that building a function is. It doesn't have to be nice. It doesn't have to be smooth or continuous. Functions generally can be as awful as you want. All it means to be a function is that when you give me an x, I give you a y. Now, we can have nicer functions and not nice functions, and calculus talks a lot about that. But ultimately, the rules for what it means to pick a function is just a table, right? It's just a table. So this thing is just a large table, right? And a large table says that for each value of x, I give you my f of x. So x1, I give you f of x is 3, 1.1, I give you it's 4, 1.01, I give you it's 7.3, right? And I just have to go through all my x's here, and I literally can choose whatever I want on this side, right? It's just a large table. Okay, we all kind of know that, so why am I emphasizing it? I'm emphasizing it because I am free to pick the value of y at a particular x. So if I have some little x naught here, and I want to pick my value of y, my corresponding, say, y naught, I can choose that however I want. I don't have to choose it based on any of the other x's. Now, if I wanted to be smooth or continuous or differentiable, then you would. But if I'm just choosing a general function, I can choose the value of y independently for each value of x in whatever way I want. And right now, all we're talking about is by building f hat, we just build different functions. And a function, you're allowed to pick the values independently. For each x naught, I can pick whatever value I want. If x is pi, I can pick the value to be e. Doesn't matter anything else about the rest of the table. It's a valid function. The only time it's not a valid function is if I accidentally put, for two different values back, or two, if I were to put, pi is also 1, then it's not a valid function, right? You can't do that. Otherwise, it's a valid function. We don't have to require any other properties of it. It doesn't have to be invertible or anything like that. Just a function, right? So we actually have a ton of freedom. I can basically build up a function point by point by point by point by point. For this x, for this x, for this x, for this x, for this x. Tell me what the y is, tell me what the y is, tell me what the y is. So when I'm building my f hat, I can do it for each of my x's individually. Okay. Why do I care about that? So let me just write that. So building f hat, right, that is choosing the optimal f, can be done one x at a time, right? All I have to do is give you some collection of f of x's across some collection of all the x's. All of the real numbers, I just have to give you my collection of f of x's, and it's just some collection of numbers. Okay, so here's my equation, my star equation. Probably someone's been screaming because I forgot part of this. There's a p of x here. Okay, there's my star equation. So let's go up here. So this was kind of an aside. Let's just write that there. This is an aside. So back to my star equation. Let's get this right. Integral. That's not a good integral. Integral. Inner integral y minus x quantity squared. Nope, not quite. Y minus fx quantity squared p of y given x. And I have a px dx on the outside, right? And we noted that the inner part is the conditional expectation, right? Which all it means is we're integrating against p of y given x instead of the joint. And the outer one is just then integrating against px, right? So this is my star, and I want to minimize this. And let's call this thing just a of x, right? Just for simplicity. So this inner integral is a of x, just a number, right? It doesn't depend on y, we've integrated out y. Again, you integrate out y if you don't forget to write dy, right? There we go. Now we integrate out y. Okay. And so if I call that inner part a of x, so it'll depend on what value of x I'm at, right, in the outer integral, but it won't depend on y because y has been integrated out. Okay, so I can write this as kind of ax times px dx. Point being that we don't need to worry about y there, right? And this ax depends on f of x. And by f of x, I mean, right, when you do an integral, you think of it as summing up over all possible x, right? So for whatever the dummy variable x is, I don't mean the function, I mean it depends on the exact value. This value f at that x, right, gives you a at that x, right? Because that shows up kind of in the formula there, right? And so a of x depends on f of x. And I want to minimize this, right? So I want to minimize this. Let's write that. I want to minimize this. That is, choose f to minimize this, right? And by choosing f, I'm effectively choosing my a, right? And I want to minimize the entire integral. But I can choose my f's independently, which means I can independently choose my values of a. So let me write that down. I can choose f of x independently for each x, right? But I mean, independently, so I can choose f of x at one value and a different value, and they're unrelated. They don't affect each other. And what that means, so I can choose, right, or I can, let's say choose, but yeah, basically choose a of x. We don't really choose it, right? We choose f, and it will give us the resulting a of x. So a of x are independently set, say, according to chosen fx at each x. Okay, that means the a of x at one value of x does not affect the a of x at another value of x, right? Because a of x is set by fx, fx is set independently, so I can basically, the a of x's can move in any way. Just because a of 1 is this one thing doesn't mean a of 5 is going to affect a of 5. They do not affect each other in some kind of real way. So I want to minimize this. That means I want to minimize this thing. So to minimize, again, let me just rewrite this here. And I'm not allowed to choose p of x, right? P of x is given to us from, the good Lord. P of x is given. Can't choose. Frankly, you don't really even know it. But we have choice here. We can affect this by choosing f of x, right? By setting f of x, right? Also, I'm building f, right? And I'm allowed to build f in any way. As I said, I can pick any function I want as my f hat. There are no rules. And so, so that I can affect a of x by choosing fx in whatever way I want. I can't really affect p of x. I can't totally choose a of x, but I can certainly influence it by choosing fx correctly. And so I want to minimize this thing. And so you could imagine that the way to minimize this, so this is the punchline, is to minimize a of x independently at each possible x, right? We want to minimize an integral, right? So if, I basically have, we can basically ignore this, the p of x. We can't choose it. It's just going to be multiplied by our numbers. It's always going to be the same. But we have some way to affect a, right? And so I'll have some function, say in the univariate case, that looks like I have x. And I basically want to minimize, imagine, let's say p of x isn't there. You basically want to minimize the integral or the area under it. And so what would you do? You would go for some particular value, let's say x naught, and you would make sure that the value of a of x at x naught, a of x naught, is as small as possible. It might not be able to be exactly 0, but you make sure it is as small as possible. And then you go over to some other one, x1, and you would make sure to choose your f so that a of x1 is as small as possible. And you do this for all your points. You'd go to another point, a of 2, or x2, and you would choose a of x2. You'd choose f, hopefully. You'd make sure you choose f so that a of x2 is as small as possible, right? So what I'm doing here is I'm choosing f of x naught to make sure a of x naught is as small as possible, and choosing f of x1 to make sure a of x1 is as small as possible, f of x2 to make sure a of x2 is as small as possible. And I'm allowed to choose these independently, right? So that was why I was making that huge point about choosing things independently. I'm allowed to set f of x1, f of x naught, f of x1, f of x2. I can set them whatever I want, and they don't affect each other, right? So I can set them in any way I want. It doesn't mean setting f of x naught to one thing doesn't mean I can't set f of x1 to something else. I can choose them independently of each other. And so what I can do is I'm going to go through every single point here, and I'm going to every x on my x-axis, and I'm going to choose f at that corresponding point to minimize a, and that will minimize the integral. And so way to, this should be want to. So I want to minimize, oh no, maybe that was right. Way to minimize is to minimize a of x independently at each x by choosing f at each of these x to minimize a of x, right? We'll talk about how to do that, but assuming I can choose f at each of my points here, right, that to minimize a of x, I'll choose f so that f at this point is to minimize a at the point, f at this point is to minimize a at that point, f at this point is to minimize a at that point, and that is because that will minimize my whole integral. This seems like it's right, so you can probably understand that this is it takes a second to get what's going on here. It's not that bad, but you have to keep in mind that I can choose all these points independently, and that choosing f is just choosing f of x at each point, right? So, so maybe I could draw the picture here. So I think this is kind of an interesting and important point to get across, right? So here's what I do, right? So at x naught, I want to minimize a of x naught, and so I'd say, oh, x naught is here, and if I choose f of x naught there, then that minimizes that, let's say. And I go to x1, and I say, okay, I want to minimize a of x1. And so I do some math, and I say, if I set f of x1 to be there, that minimizes it. And I do this for all my points. At x2, I say I want to minimize a of x2, and if I choose maybe, maybe this f of x2 there, and I'm allowed to choose that independently of the other f of x0 and f1, that minimizes it. And I do that for every single point here. And eventually, if I do that for every single point, I'll eventually build up some function, right? And maybe the function looks like that, right? But all building up the function is just at each point in this axis, I choose the corresponding point here. I choose, right? You do that. So the way to minimize this quantity, which is just a simplified version of our, simplified, but it's the kind of nice version of our risk, is that I choose the value of f, that is f of x, at each x to minimize a of x. So that is, the way you write that in math is that f of x, f at x is chosen among all possible values I could put for f of x, so that it minimizes a of x, or if that's supposed to read argmin, let's go back up here, right? What is a of x? It's the expected value of y of this thing given x, right? So it's basically it is expected value of, I'm going to write it this way, y minus fx squared given x. And indeed it is given, it's even more than that. It's given, let me rewrite it. It's expected value of y minus f of x squared given x is little x, right? So f of little x, right, this quantity, I'm going to choose my value of my function at little x, so that when I minimize, that I'm minimizing what I was calling a of x. A of x is exactly this, right? I'm choosing among all possible values of f of x, that is f at little x, to minimize this thing. this is what we're calling a of x, right? Or a of little x, right? If you look at what a of little x was, it's the integral of y minus f of x, right? So I replace my capital X here with my little x. I guess this should be a little x, right? That is exactly this thing, right? So the punchline, this is the punchline. The punchline is that if I want to get f of my f, I want to say, what is f at some little x? And right, remember what this f is. F is this learning algorithm. Is this learner, right? Right, f hat, right? I guess I could call it even f hat of x, right? So my best thing to choose, my f hat, is if I look among all possible values of f of x, the one that minimizes this conditional expectation. And so what have I done here? What is the real punchline? I've made a big hay out of this. I ignored, if you go back up to this, if you look at our original thing, it's the expected value of x, expected value of y given x of this thing, right? I've ignored the outer expectation. I don't actually have to care about the outer expectation. All I need to do is care about the conditional expectation of y. So this is big star, the punchline, which is that if I want to choose my optimal, right? I guess this is not the final punchline. We'll have one more punchline here, but if I want, then I minimize this, okay? And we can actually calculate what this is. So here's a cute little fact, okay? So just as an aside, if I have a random variable z and I want to minimize, let's say a hat is the a that minimizes the expectation of z minus a squared, where z is a random variable, okay? How do I do this? Well, this is a Calc 1 problem, right? Expected value of z minus a squared, you can square this all out, z squared minus 2az plus a squared, and this is going to be expected value of z squared minus 2a expected value of z plus a squared. And I look at the derivative with respect to a, right, of this bad boy. With respect to a, the expected value of z squared goes away, doesn't depend on a, I get negative 2 expected value of z, and a squared becomes 2a. I set that equal to 0, and I solve for a, and I get a hat is the expected value of z. So that's key, right? So this is okay. So what does this fact have to do with anything, right? If I want to minimize z minus a squared, I want to find the a that minimizes this, I choose the expected value of z. So the best thing to do is to plug in here expected value of z. Right, that's all that says. So what does that say about this, right? We said that f hat of x, that is the value to choose for f hat at some little x, is the value f of x, we could call it a, it doesn't really matter, that minimizes this is this how I want to write it? I don't want to write it that way. Let's just keep it how we had it written before, right? Less confusing, right? Okay. It was to minimize this, and so by the above logic, this, right? Well, now we have a conditional expectation, but that doesn't change much. So let's just tack on that conditional thing. And it was, before it was z minus a. So if this y, it said were z, and this were a, this would then just be the conditional expectation of y given x. Now that is the punchline. So let's just real quick recap this. We wanted to, so this is our basic statistical learning, right? We minimize the risk. We wanted to figure out what that was. Turns out you can do some algebra and you can use calculus and some probability. You can write this as an iterated expectation, right? And turns out you can make a little bit of a complicated argument. It's actually not too bad that we actually can ignore the outer part of that iterated expectation and just focus on minimizing this inner part. And which is a conditional on x. And it turns out, because we're using this squared loss, that they're a kind of similar argument to this, that if we want to minimize the squared loss conditional on x, all we have to do is that the optimal thing to predict at x is the conditional mean of y given x. So let's just sit and let that sink in. I want f of x, or f hat of x, is supposed to predict y well. If we use a squared loss, what that tells us is that the best thing to do is to predict at some little x the conditional expected value of y given x is at that little x. That's remarkably simple. Just as a fun fact here, if we had instead said L of f is like the absolute value, right? Something like that. So people always go, well, what happens instead of we use a square, we use an absolute value? You can show, although I will not, that the optimal predictor would be the median of, instead of the average or the expectation, it would be the population median of the conditional distribution of y given x. So it would be that conditional median of y given x. So that's really cute. So you can do this with other losses. There's a little bit of, so the fact that we use a squared loss led it to be the expected value. If you use a different loss, you could come up with different optimal f's. And of course, there's a whole literature about what the best losses are to use and what different losses do for you. We'll talk about a hinge loss later in the course. We talk about SVMs. So how does this relate? Because this is kind of a bunch of theory. How does this relate, right? So what we saw is that f hat of x, the best thing to do is to predict a conditional mean of y given x is some little x, right? So this f of little x, right? Okay. So this is our golden rule. If we use a squared loss, that's the optimal thing to do. So, okay. What do we actually do in practice? In practice, we approximate, right? Just like how we said that we approximate the risk with an empirical risk. In practice, we don't actually know how to calculate that. If we knew what the probabilistic distribution is, we wouldn't need to solve the problem in the first place, right? How do we approximate? Well, right? Step one is collect some data. We call this the training data, right? That are draws from our distribution, all right? We don't know what the distribution is. We want to do some inference on it. We want to figure out what this conditional expectation is. So collect some data and approximate this, right? And so step two is approximate this thing. And you call it your f hat. How? How do we approximate this? This seems weird. We've already done it twice. We've talked about two methods. Here's one way. Let f hat of x be an approximation of this conditional expectation. How would I do that? Well, expectation is kind of like an average. And so what if I just average all the values of y whose x's correspond to little x? But I might not have training data where my x is exactly equal to little x, so maybe let's just pick stuff nearby, right? So let me say that this is the average value of my y-ends for x-ends near x, near my little x. And maybe we'll say, let's use the k nearest neighbors to x, right? So I'll say it's nearby little x if I just choose the k training points that are nearest to it. And so I'll approximate that as the average of these k nearest neighbors, and I'll choose, I'll sum over my training data where x, the x sub n's are, in the k neighborhood of my x, and I'll sum up the y sub n's. That notation sucks, but that's what it is, right? Of course, this is called k and n. So k and n can be viewed as trying to build the optimal classifier by approximating this conditional expectation in a certain way. The certain way is, well, I'm just going to average, a conditional expectation is like the average of the y's when x is little x. So what I can do is kind of average the y's when x is kind of close to little x. So, pick the nearby ones. It's called k and n. So that is way one. Here's way two. Way two is assume some structure of this conditional expectation, and my structure is going to be that it's linear. So let me say it's some linear structure, which is that the conditional expectation of y given x is linear, and so we could always write linear as some inner product. Let's say it's some x times beta, or x transpose beta. And then I estimate. So all I have to do now is I estimate the betas as beta hat, and my f hat is just beta hat transpose x. So this first one was called k and n. If instead the way I approximate it is say, well, I'm not going to approximate it with this local assumption. I'm going to have a strong global linear assumption about this conditional expectation, we get what we call linear regression. Right? And that's exactly what it is. So that's some nice little theory to pull things together. I think people often, when they teach this kind of course, there's a kind of pull to teach as a very topicsy course, but I think teaching some of this theory, and we're gonna now, after this lecture, we're gonna get back more into kind of the trenches of actually talking about some methods, but it's nice to do a little bit of theory just to pull this together. And even if you can't recapitulate the proof, you can remember that what the result is, which is that the optimal thing to do with a squared loss is predict as f hat is basically predicting the conditional expectation, and so k and n is approximating that conditional expectation in one way. Linear regression is making this linear assumption, which allows us to approximate in another way, right? So that's kind of regression. Let's spend the last kind of 15 minutes here, 10 minutes here. Let's talk about classification. So we have our hierarchy here, which is stat learning, or machine learning, and we have supervised problems, which we have talked about so far. We have unsupervised, which we will talk about later in the course. So supervised, we have training wise. And this we have no training wise, is one way of thinking about it. Under supervised, we have regression, which is basically continuous problems, and we have classification. And we've just talked about kind of two methods of regression and a whole bunch of of material, which will allow us to build up more regression methods and kind of put them in context. And what we want to do now is talk a bit about classification. So we'll talk about this up through, say, the midterm, and then after that we'll start talking about supervised, and then we're just going to be all over the place. So examples of classification. Classification is, I want to predict. It's basically anything that's the response, the Y is discrete, or maybe categorical. So categorical Ys. I want to predict song title from sounds. It's like so what SoundHound does, right? I have a large but finite set of song names, right? And they're kind of categorical. There's no particular way to order them. And let's say another kind of problem is predict tumor as benign / malignant, right? So this is pathology. I maybe want to predict a protein class. What kind of protein? Maybe it's alpha helix, or maybe it's beta helix, or maybe it's a random coil. So this, we have three different classes. Tumor is what we call, this tumor one we would call binary classification. We have two classes, two-class problem. This is a three-class, and this you might call a multi-class. I have tens of thousands, but a finite number of songs that I want to predict from. So the setup for classification is pretty similar to regression. The statistical learning setup is that, again, we have some training data, some y-ends, we have some x-ends, and our x of n's are, p-dimensional numbers, features. But now, where our y-ends before were real numbers, or numbers, we now have the y-ends in some capital C set of classes. So this is my capital C, and this is some set of discrete classes, class 1, class 2, class 3, all the way up to some class capital K, let's say. That way we want to use K. Sure, why not? We use K all over the place. But so this is my set of capital K classes. All the possibilities, but it's discrete, and there's no real ordering to them particularly. Our goal, right, is to find some f hat so that y hat, which is going to be y hat will be C1 or C2 or C3, right, is one of these classes, which is f hat of my x, let's say some x, is approximately whatever my true y is, right? So y is in my set of classes, x is some feature vector, and so pretty similar. So all I've basically changed that the y's are now a discrete set of classes instead of being any number. And I can ask the same question for the classification setup, which is what's my optimal f? Fear not, we're not going to spend forever deriving this, but we need a loss for this, right, for classification. We had our squared loss for regression, but you can't really take a difference between discrete, categorical variables. It doesn't make sense to take, what does alpha helix minus beta helix mean? That's not, you can't assign a meaning to that. And so since our outputs are y's, they're not numeric, they're classes, you can't, really use a squared loss for taking difference. What we use is called the 0-1 loss, and it says that the loss of f is the indicator that f of x is not equal to y. So what does that mean? It basically means I'm going to give it no points of loss if f of x is equal to y, and I'm going to get a single unit of loss if f of x is not y. Right? Y is the target, f of x should be y, so basically I'm just going to assign some unit of loss that way. And let's see if we can do this. Do this here, right? We know that f hat is, or let's say f hat of x is what we minimize. We can make a similar argument, let's say, where right? So last time, instead we had the squared loss, right? And you can make all the same arguments, it doesn't matter what the loss is, up to this point. We can basically, instead of that squared loss, we saw that we could minimize, which we said before, we can now minimize, for the classification problems, we're going to minimize this what's called the 0-1 loss. So this thing is called the 0-1 loss. And so the aside here is that the expected value of the indicator, let's say that x is an a, let's say something like that. What is that? That's the integral for, say, a univariate random variable of indicator that x is an a times the density of x dx, which is the same thing as the integral over a, because it's 0 when x is not an a, and it's 1 when x is in a. So that is an equivalent statement, right? And that is just the probability that x is an a. So the expected value of an indicator is just the probability of the indicator, of whatever the statement is in the indicator. Brute factor probability. Expected value of the indicator is the probability of where the statement is in the indicator. Basically, because when you write this out, the expected value is this, and this indicator is just 0 or 1. When it's 0, we ignore it, and it's 0 when outside of a. And when it's 1, we just get p of x dx. And so we're just going to integrate over a, and that's the same thing as probability. We're integrating p of x over a, the same thing as probability that x is an a. So this, which is very similar to last time, but now we've replaced our squared loss with our 0-1 loss. We can say it's the same thing as the probability that expected value of that is, now we can just say it's the probability that f of x is not equal to, y is not equal to f of x, conditional. All right, so this conditional probability. And let's see. So I could write this as 1 minus the probability that y is f of x, conditional. That's certainly allowed. So probability y is not equal to f of x is 1 minus probability it is. And so I want to minimize this whole thing. So I want to maximize this, right? And so alternatively, if I want to maximize this, this is the same thing as the argmax picking f of x that maximizes this probability. And this, we said, was our optimal f. So I did that pretty quick, but I spent a lot of time in the first one, so I don't want to belabor the point too much. So this is what's called the Bayes classifier. And it came from the fact that we chose a 0-1 loss, which is basically saying we're going to get the Bayes classifier. That would be the optimal thing to do. So what is the optimal thing to do? What does this actually mean, right? What I'm doing is I'm saying, given I've observed a little x, I'm going to calculate the probability in fact, I could simplify this even more, right? Because my f of x's are just classes. So I could even just say this, right? This is going to be easier to interpret. What it's saying is that, right, because my f of x is one of my classes, right? F of x in this case is predicting either like C1 or C2 or C3, right? It's predicting the class, right? That's our setup, right? Where's our setup? Our setup is here, right? We want f of x is going to be about y. Y is one of our classes. F of x is predicting, is it C1, or it predicts it's C3, right? Predicts is one of the class. Predicts is alpha helix or beta helix, right? So f of x, I could just, is some class, right? And so you can interpret it this way, or you can rewrite that f of x is just some class, right? And what it's saying is that what I'm going to predict, that is f hat of x, my best thing to predict, this so-called Bayes classifier, f hat, is that given I've observed a little x, I'm going to predict the class, that is f of x, to be the class that maximizes my probability. And so the idea here is if I have, I'm going to say, so the idea is that I see my little x, and I'm going to calculate the probability that y, that my output, that my y is class 1, given I see my little x, and I'm going to calculate the probability that y is C2, given I've observed my little x, and I'm going to calculate the probability that y is the third class, given the little x I've observed, and then I'm going to pick largest here. So I'm going to pick the one that's largest. And that's the Bayes classifier. So but it makes a lot of sense, right? All you're doing is you're saying, I'm going to pick the class that has the highest probability. So, of course, you need some way of approximating these probabilities. And the first way, so just like how our regression methods you could see is approximating a conditional expectation, you can view classification methods as approximating those probabilities and then picking the one that's largest. And so what K&N classification does is basically the same way it worked for regression, it's going to work for classification, which is that what it's going to do is if I have some training data, so here's my training data, maybe I have some red squares here, so these are my classes, maybe I have red squares, and so this is basically like my x-axis, right? And I have green circles, and maybe I observe some green circles, right? So for this value of x, I observe a green circle. This value of x, I observe a green circle. This value of x, and then I have, let's say, blue triangles, right? And something like that. Maybe those are my blue triangles end up there, right? And if I have a new point, I want to classify at some new point. So maybe my new point is here, right? What do? I'm going to look at my neighbors for my K&N classification. I'm going to look at the K nearest neighbors. let me write this out. It's the majority class among my k nearest neighbors. So if, for example, k is 3, and I'm predicting here my 3 nearest neighbors are maybe these 3, and in this case, so corresponding there, my f hat of this x would be green circle. That's my class. Predict it's a green circle because it's close. The closest points to it are a green circle. One way you can write this out is as the following. I'm going to say p hat of my class is going to be the probability y is equal to that class given my x, and I'm gonna approximate those class probabilities, which is what we call these things. We call them class probabilities. And I basically need to calculate all these PC hats, or PCs, and I'm gonna approximate them as the percentage of the k nearest points that are of class C. So let's see. My notation is I'm going to look over n, where the xn are in the k nearest to my x, and I'm going to look at the corresponding training y's. I'm going to see if they're in class C. So, right? So our Bayes classifier says that what I do is I calculate the class probabilities. Probabilities class 1 given my x, class 2 given my x, class 3 given my x, etc. And I pick the largest. I pick the class with the largest probability. So k nearest neighbors says I look at my nearest points and I pick the class that has the most among my nearest points, right? So another way to interpret that is you could calculate the class probabilities, and this is kind of the formula. What it be is the percentage. This is a fancy formula for saying percentage of k nearest neighbors of class, whatever, my class little c, whatever that is, class 1, class 2, whatever, right? So this is the formula. It's a little kludgy, but it's basically sum up how many, this is how many, this is number of class C, right? I look at all my y's. Is this a class C? Is this in class C? Is this in class C? I take the total number in class C of my k nearest neighbors, and I divide by k. That gives me the percentage of my k nearest neighbors at class C. I call that PC. That is my class probability. It's an approximation of the class probability, and I pick the largest. Or I pick f hat of x equals class with largest. All right? But that's exactly what my Bayes classifier said to do. So you can interpret this k and n classifier as exactly doing that, as approximating my class probabilities and then picking the one with the largest. So I think this is probably a good place to stop. I went through that a little bit at the end there pretty fast, but k and n is pretty simple, right? We're just going to look at each point and we're going to predict the class to be the majority class of the nearest neighbors, just like we predict the x as the mean value of the nearest neighbors. Now we're just going to say what's the majority of the nearest neighbors. The majority are green circles. We'll predict a green circle. If I were predicting a point over here, I would probably predict it to be a blue triangle because the majority of the neighbors are blue triangles. And you can view it in this way as approximation of those. I mean, no one actually computes it this way, but you can view it as an approximation. It is approximating this class probabilities and then picking the largest one. Okay, let's stop here.